Doctor, stage is yours.
Okay. Yeah, thank you very much. My name is Stefan Kniesburges. Together with my colleague and boss Michael Döllinger, we are actually working at the medical department in Erlangen from the university there, and we are part of the ENT department, so ears, nose and throat. But we are dealing with the aerodynamics in respiratory systems, so especially in the larynx. There we have to face turbulence, fluid structure interaction. The two vocal cords are oscillating with a very high frequency, and there was, I think, a day 8 years ago where we just thought about how to get students and how to get topics for students. And as Michael is a surfer for almost 25 years, and I'm a mechanical engineer with the focus on aerodynamics, aeroacoustics and that stuff, we just thought, why not simulating the surfboard or some surfboard fins? And then we are started, and it went on. Actually, our goal was to have at least one publication. Michael wanted to have it in his bathroom, but now we have a few more because it's so interesting, and so just from the physics. And I just want to give you today some insights in our work. I hope I can explain it that everybody is understanding. But though this is actually the outline of my talk, so first the major focus today is the surfing hydrodynamics, how we try to measure it or how we measured it. I will start with some CFD simulations as we started, as I told you just before, and then I will come to the experimental study on surfboard. So we try to measure during surfing the pressure at the surfboard fins. Done with that, I also want to give you some impression about our work of simulating the river wave in Nuremberg, the Fuchslochwelle, which we try to optimize with several focuses, and this will be the end of my talk. So let's start with our simulations. So the very beginning of our interesting side project beside the medical stuff. So we started actually with a quite simple case. So we had a 3-fin configuration. Here you see the right side fin and the center fin, and we placed it just in a box full of water, and we had an in stream from the left hand side, and then we just increased the angle of attack, which is actually the angle here between the inflow and the axis or the chord axis of the fin. And then we increased it somehow, and then we found some nice separation areas, so recirculation areas when the flow is separating from this fin. It's quite similar to wings in planes, where we also get, or where you do not want to have some flow separation, because then the plane is falling down without any resistance. And what we there found is that we have here some flow structures, vortices, which are separates here and are pushing this center fin. And we found that there is a force which can act on the center fin if your angle of attack is too large, with a frequency of about 14 Hertz. And we heard of a guy from Wollongong who really tells us, yes, he sometimes experienced some shivering in the back, which could be somehow this effect. So this was quite similar simulation case, and if you want to learn more about that or read it, you can just scan this one, and you will get the publication in the Journal of Fluid and Structures, where we could publish our results here. So the second one was then a 4-fin configuration, where we measured the drag, the lift, and drag to lift coefficients. Those coefficients are also quite similar to those of plane or wings, where they just try to calculate the lift force by which the plane is lifted up in the air, efficiency and that stuff. And we also use those coefficients or those parameters in this 4 fin configurations, and you also in these configurations you see large interactions between the single fins when the angle of attack is high enough. So also for this one, please scan this and you can read the paper and get more information about this one. Then another study, it was also a student project. A student found this video. It was Gary Lopez at the Kelly Slater farm, and what he did is he just surfed very constantly without any change at this wave. And then the students just told us he could try to somehow measure the position, so how the surfboard is constantly positioned on the surface of this wave. And then he wanted to calculate the gravity force, where the gravity force has to be at the surfboard, which was acted by Gary Lopez. So the gravity force by Gary Lopez, where does this force has to attack on the surface to get this position. And so he set up an CFD simulation with a free surface. He put here a surfboard on the surface, just hold the position constantly, and then we had here the lift force. I just started again. We had here the lift force in blue from the water, and this is the gravity force. And then he developed an optimization, mathematical optimization algorithm, which varied the position of the gravity force, which is here the red one, so long that he could find a place where no force is acting in these 2 directions on the surfboard. And so the surfboard is fixed on the surface, and when he found the correct position where he has no force in these 2 directions, then that would be the point where the gravity force acted by, or which was pushed on the surfboard by Gary Lopez, had to be for this video. And this looks like that somehow. So here you have the force balance in Newton, and you have the force in x direction in blue, and this dotted line here, and this orange one is in the y direction, and the other 2, these 2 lines are actually the positions in x and y direction where the force has to act. And what he did, he simulated one position, then he just evaluated the balance, the forces. Are the forces not 0, then the force would be somehow positioned in the next place. And this was done for a lot of simulations, and here at the end point we got both forces almost to 0, and then we had the 2 positions which are at the very end of the surfboard. So this was also a student project which we tried to publish soon, but yeah, so those works were our motivations to think what can we do in the next place. And therefore, if you are doing those CFD simulations, it's purely done in the computer. And you have, so if you want to publish this one, then you have reviewer, and the reviewer will ask you, okay, it's only computer simulations, is that valid? Is it correct? Did you do correct modeling? And therefore you need to have some measuring data. So data which were measured, and you can say, okay, here we measured velocity. The velocity is similar to which we have simulated, and therefore you can validate it. Also, we cannot simulate every surfing maneuver or something like that. We cannot simulate everything because it's too expensive. So we need to have some real surfing or measurements in real surfing situations. And therefore we started now with our project of the experimental study, and we tried to measure, or we measured actually, the hydrodynamics on surfboard fins. We took an ordinary FSC fin geometry, then we implemented here some box in it which is sealed up by this rubber ring, and then we placed here very, very small pressure sensors at the inside and the outside, so on both sides of the fin. I will show you later on. Here's a photograph of this configuration. Here are the sensors, and they are then connected by wires which are fed through the foot of the surfboard into the surfboard, where we then had to implement some electronical acquisition board where we can measure or acquire the pressure during surfing and to store these pressures, so we can make an analysis later on. So this surfboard or the whole surfboard looks like this. So we used the two fin configuration, so we left out the center fin not to have any interaction with I showed you on the second flight. So we want to avoid those interactions, so we want to have the pure flow passing one side fin. So we took the left fin in our surfboard and equipped them with 4 pressure sensors, 2 at the outside and 2 at the inside of the fin. So please remember this nomenclature, that we have the outside surface and the inside surface, because that becomes important in the next slides. What is also quite interesting is that if you are looking on the cross section, so if you make a cut through this fin, we have here an pretty similar profile as a plane wing has. So we have a curved outside surface and a flat inside. So this becomes also quite important when we will have a look on the measured data. So this is actually the acquisition board. The student who worked on this project developed. So we have a controller which where the program, so the acquisition program was stored and was performed on it. Then we have a multiplexer which is connected to our 4 pressure sensors. Then we have a storage, and of course we need to lithium I have no idea at the moment, but it were lithium batteries just to have the power. And this was then assembled on such a board, so an electronical board, and this was then implemented in the surfboard and worked autonomously after we started the program. So the implementation looks like this. We had a very old surfboard, and we had to cut a large hole in the tail, or in the rear end of the surfboard, to put in the board there. Then we have here another channel which goes directly to the mount of the left fin. Through this channel, the wires were fed to the acquisition board. Then everything was sealed up some nicely, and then we put in a box, an ordinary box coming from the electronics, which is also watertight, and therein we fixed the acquisition board, and this could then be somehow connected to a computer, and then the computer started the algorithm. We have to seal everything up, put the cap on top of the box, and then the surfer could surf, but I will show you in a video later on. So first of all, we had to test the system, and we did this in an ordinary water tank. So we have there a water tank, we have here some scale or a rule, the acquisition board actually, and here is some prototype, so not an entire fin. It's a prototype which is actually, well, looks like this one. Here we had just the middle, so the middle hole for the pressure sensors equipped with a sensor. We had 2 sensors, one sensor there and one on the back. And then we did some ordinary tests. So we had a static diving test where we just dive the pressure sensors at a certain depth. And by this equation, so this is actually the pressure as a function of the depth. This is the density, this is the gravitational constant, and this is the depth of water which we can measure. And there we can see that it's quite linear, or we get a quite linear measuring signal, and it follows really this rule described by this equation. Then another test was a dynamic diving test, so we just randomly dived this prototype up and down. We recorded that with a video camera, and at certain positions we just checked the depth calculated how large the pressure should be, and then compared to the experiments, and that was also quite valid. And then we went on to the Fuchslochwelle to check whether our system is working during real surfing. And so actually, this was the whole setup. You see here the wave. This was Nina Punger, the master student who wrote her master thesis about this topic. This is Dr. Boaz Stur. He's a former PhD student. He just finalized his PhD in the beginning of this year. And at the moment, they are actually sealing up the box. So they just started the algorithm to measure. Then we had 5 minutes to measure. Then the storage was full. And now, when I start the video, you see that the cap is on that box, so it will be fixed by screws, and then afterwards it's additionally sealed with some gaffer tape, just to be sure that no water is coming in the box, but because this would be not that good, and it's at the tail of the surfboard, so it's pretty probable that water is coming just on the top here, and when this is not tight, then we would have a problem. But it worked so far pretty well. And the surfer was sitting here and had to wait until everything was prepared. Yeah, and then we asked a surfer, it was Thorsten Keck, to perform very nicely and smoothly and equal turns. So as many as he could, and he did a quite good job, you will see. And then we made, additionally to our pressure acquisition, a pressure measurement, we also made a video. And this video was synchronously started with the pressure measurements. So we really had the stream which was synchronous to our pressure measurements, so we could relate the position of Thorsten with the surfboard to a certain pressure value, and this is quite important, as you will see later on. But let's observe Thorsten surfing here. So it was really quite nice and quite slow and not that sharp turns, so as we requested. So I think that is a big applause for Thorsten. Without that, it would not have been.
20-kilogram board.
Yeah, that was true. We had some other guys, for example, Michael, but so we need to add Thorsten because Thorsten is very large and his weight is much higher, so he can manage this board. Other guys were too, so the weight was not large enough to manage this board on this wave. So actually, this was quite a quite good factor in our experiment. So let us come to the results. So first of all, we fragmented the video. So we split the video up in all the single pictures, and then we had our time frame, which is synchronous in both signals, so pressure signals and video signals. And then we found, we searched for moments where in the middle of a turn, so when the surfboard is parallel aligned to the main flow direction. So as it is in this case, or in this case, and so on. So we have 7 turns, and we had the time points where the surfboard is aligned parallel to the inflow. And this is actually marked by this arrow. So at this point, at this time point, this figure was recorded. And the next time, but in between these 2 time points, we have these traveling regions where Thorsten traveled from one side to the other. And if I now show you the pressure signals, so the other signal actually then, so this diagram is actually the relative hydrostatic pressure. So it's the pressure relative to the environmental pressure. So the difference between the pressure measured and the environmental pressure, so the normal air pressure which exists here on Earth. The x-axis is a time axis, so the same period as I showed you with the pictures. And then we had now 4 pressure signals. At the outside, it's in blue and red. So these 2 graphs are the pressure at the outside, the curved outside of the board, and green and yellow is at the inside. And the first thing was we were quite happy that we got really a nicely periodic and systematic signal. Because we had at the turn points, so where the board is parallel to the inflow, we had a really small pressure difference between the 2 sides, between inside and outside. It was really small. But during the traveling, so just in the traveling periods, we had the largest or a very large difference between inside and outside. The only thing about which we were surprised was that it stays the same, without any dependence on the direction where he traveled. So it's the same for a right travel to the right, travel to the left. It's the same. And actually our expectation was that it has to shift somehow. So that during left it's looking like that, but then for right, blue and red had to be positive and these had to be negative because it's the other way around. And we are just wondering why this happens. And therefore we just made here some schematical sketch. So these are now two zoomed up periods, or at three turns with 2 traveling periods. And the board position looks like this. So just remember, it's not the case that the board is going to the right. It's just the time axis. The board is standing there, but just for a better display, it looked like that the board is going to the right-hand side, but it's actually standing there and going on the same position to the left and to the right side of this channel. When we now zoom this up a bit and looking on the inflow to this left fin. So this fin was equipped with the left fin. Here we have the pressure sensors. And then we are looking just at the turning points where the fin is parallel, or where the board is parallel. Then we see that the flow direction is actually the flow coming from the wave, nothing else. So it's in every point the flow which is coming from the inflow. But during the traveling, we had another component, and this is the component Torsten had when he travels. So actually the velocity Torsten had during the traveling. And therefore we had to do some vector addition, and we get another component. This is the actual component which acts during the traveling on this equipped fin. And if you see that it's somehow directed in this, so from this to this side in this way, and this is the other way, then you see it's not that different. It's not that different. It's nicely aligned to this wing, and therefore it's not that surprising that actually this difference looks the same. So we have the inside with a higher pressure at the inside and the outside with a lower pressure. And why is this the case? Because we have here actually a curved outside and a flat inside, as it is the case for a wing at aeroplanes. And you know that the wing of an aeroplane, the upper side is curved, the inner side is not that curved, and therefore we get a lift force. And that is actually so we get a lower pressure at the side above, at the upper side, and a higher pressure at the inside. And this pressure difference, which we actually see here, this gets the aeroplane into the air. But here in the surfing, it's the other way around, because the wing is actually aligned in a vertical direction. So in this case, we get a lift force to this direction. And if we assume that on the other fin the same happens, then we had there the opposite force in the other direction. And our assumption was then that these two lift forces actually stabilizes the rear end of your surfboard. So you're standing there with your back foot, it doesn't matter of the left or right, and these two forces acting to the outside are stabilizing the rear end, so you can have a very stable rotation point and can actually guide your fin with the forefoot, which is not stabilized because there is no fin in it. And that was then our interpretation about the pressure centers which we measured there. And in the beginning of this year we could also publish this in scientific reports. And if you want to have another check and maybe read what what we wrote there, you can make also a photograph and then had a closer look to this one. So that was actually our current study, experimental study about surfboard hydrodynamics. The other thing which we are doing is simulations, so CFD simulations of the river wave in Nuremberg. And our motivation is actually to optimize the shape of this configuration. And we are focusing on the wave itself, so to improve the wave, actually to increase the wave height. And what we also found out is that this region just downstream of the wave, just behind the wave, it's quite turbulent and it's quite uncomfortable, especially for beginners, because here you have a high mixture, turbulent flow with high entrained air and so on. So your lift, so your natural lift of your body in the water is decreased. And as this is very unstable, we tried to somehow stabilize this one beside the wave. So we had a study. It was the first study. It was in 2023, which we started by CFD. So this is actually a plot of our river wave there. You see the river Pegnitz. This is the Pegnitz, and they just digged here a bypass. And here is the actual wave module. So it's a ramp with a kicker, and that pushed up a wave where you can then surf on. And actually this down there is the region where you fall in and where you have to swim to the sides and to the land again. First of all, we had to develop a geometrical model about that. It was quite funny because we know the geometrical dimensions of this river or this wave module quite well. So we have CAD data about that one, but we did not know how, for example, this looks like. So we know here the contour, or we know the land. That's quite up the depth. We had no idea about the depth and how many stones are in there and so on. So our master student had to dive there and had to measure actually just before how deep is it. And we made some grid points where he measured the depth of water, and with that he could then generate this basin or this region, this outflow region there. And the same was done here at the inflow. We also had no idea because it was not made with beton or something like that. So it's purely stone, sand, and something, and everything what exists in rivers. And so he also had to measure the depth. But then he got this this geometry in which we can then perform our CFD simulations. And then we just considered what can we do and what can we implement in this wave module. So this is actually the situation we found when we started with the CFD simulation. So we had here the main geometry, and here are some inlays positioned in. these inlays were also for safety reasons. I can show you later on. But this was the position we found. And then we just thought, okay, how to somehow manipulate the flow, and then we decided to plug in some baffles or some fins in it to disturb or to somehow manipulate the flow. So let me start with the configuration we found. So we had here the inflow coming from the left-hand side. Down the ramp, we had a really high velocity. This velocity then went into the basin, or into this wave model, was deflected by this kicker to the upper side, and then we had a really fast flow stream here, which then generates a large recirculation area which pushed up actually the wave where you can surf at this side. But then this high velocity stream goes down to the bottom, stayed at the bottom, and this was the reason that we had here this really large highly turbulent and unstable flow field where we really have to, or where it's really hard to get up to the surface when you fall into the water, and which was quite uncomfortable for even for beginners to handle them after they fell in. But if we now just include at this position some fin, so some fin-like structure, some baffle. It's also seen here at these positions. Then the thing happens that this high velocity stream went down and was then pushed up again to the surface of the river there. And by that we generated a very stable recirculation area which stays here, is not moving anywhere, it's just staying here. And if you fall in here, you will be in this region and pushed up again or by the stream to the surface. And we were quite convinced that this will work well, and therefore we made a check. We installed, or actually the guys from the wave installed then such a baffle. It is somehow varied, so we just cut this really sharp edge at the top of this baffle just to decrease some injury risk and something like that. And then I can show you here just a comparison between the flow field with and without baffle. So here in this picture or video, you see that it's quite turbulent here. It's no coherent structure. It's not stable somehow. And in comparison, this is the case with the implemented baffle. You see that when the surfer surfs to one side, goes to the middle, and then he jumped in and came immediately up to the surface. And the other thing is that if you are looking at this region, you see these bluing up of the flow which comes up again to the surface. So what we simulated worked quite well in reality, and this was really quite motivating to us to have further studies and to do further simulations. This was also published in a scientific paper. Just make a photo and you can have a read of that one. And then last we had a second study which is actually at the moment still in progress. So with the first study actually we optimized this region just behind the wave, and the second study had now the motivation to increase the wave height. And we did a lot of configurations, so we had a lot of ideas how to do that one or to get the goal or get to the goal. But these are the two best configurations so far which we have seen. The difference to the former configuration was that we decreased the height, so this dimension of the inlays. And then we even tried to reduce this inlay by half. So the distance, so the height was decreased by half, and also the length of this inlay was decreased by a half. And the result was that if we just come back, that we got here a much better development of this large reticulation area. And you will see in the last slide that it really helped to push up the wave even more than compared to the default well or to the initial conditions. Here we have two different, or we have such an under configuration or a second configuration where we just released this fin there just to see whether we need this fin or not. And just by this comparison, you see that we are, even at this configuration, we had this typical flow, which is then at the bottom. We have this unstable field. So it was clear then that we need this waffle here to have this stable one just in place. But we could increase here the wave height. I will show you later on. The second configuration shows actually the same. But if we now had a look on this diagram, here you see the average wave height, which we measured in the simulation for a lot of configurations. And I just want to show you now, this is actually the wave height from the initial condition, so it's about 0.65 meters. Then by implementing this baffle here, we could even increase, although it was not our motivation at this point, but we could even increase the wave height at this point. But with the new configuration, this is a configuration where we just reduce the height of this inlay. We had really the largest wave height at about 0.82 meters. If we let out this baffle, it's much lower. So actually, this is really the confirmation we need this baffle to have a good wave height. And this is the other where we also reduced the length of this inlay, which is also not that good as if we just release the height. So this would be the next idea, or this configuration would be the potential configuration which we can try in reality at the rivers to even increase this wave height. And I think with this I'm done. So here are our contact dates. So if you want to know something, have some additional question, you can post it by email or send us an email, or if you scan this, you will also have our contact dates or telephone numbers and all that stuff. And with that, thank you. And if you have some questions, please.
Any questions?
First of all, thank you. This was a really interesting investigation and talk. Thank you so much. Actually, I have plenty of questions, but I'll maybe reduce it to 2 or 3, and maybe we can interview them later. First of all, I checked in parallel when you go to this scan. You cannot really download the study. You only get snippets. And then you have to fill in your association name or so. Maybe you can later tell a little bit so everybody has a chance to really download it, what he would have to fill in.
I could check it, yeah.
Yeah,
of course.
No, I almost forgot the questions I wanted to ask else about it. I think it'll come in a second.
Maybe I have a question. Lots of waves, and natural question is, let's say that we would like to emulate our wave over here. What it takes, how difficult it is for a regular guy, or is it really like high-tech academic stuff to do some, let's say, measurements or modeling the impacts of changing the wave?
So measuring the wave, measuring it's quite difficult. So we're also thinking about how to measure flow speeds in the wave, or how the actually flow field in the field looks like. And to measure it, it's therefore quite different, because you need to have a sensor which you have to hold in the water. And there are the concepts by which you can, or with which you can measure, for example, velocity or pressure, but you will have to handle the vibration of this. So you have water in a high velocity, and no, you cannot have a really rigid mount for some sensors which is not moving somehow. So this is quite challenging. For the simulation, you would need to have the exact geometry actually. So as I said, in this river wave in Nuremberg, we had for the wave module it was quite clear because we had very exact geometrical dimensions, but not for the inflow and the outflow regions. So there you need to have some solutions for getting the contour of the ground, for example. So this is something, but this is not the difficult one. The difficult one is then to have you need to have the correct simulation software. Those software are quite expensive, and then you need to have a high performance computer, which we have at the university. So this can just give you some impression how large it takes. So for simulating one configuration of the wave, we need 12 hours. And we are simulating on about 640 single processors. So this is yeah, just the calculation. So without analysis and something like that. And this is so we can do it because we had to supervise master theses and so on. So just for the education of the students, it's quite cheap. But if you do that commercially, it's quite expensive.
And so it means that you have to do initial measurements, and this is the input for the model, and like onwards on modeling.
Sorry?
Like, do you need the measurements of the current state precisely done in order to have an input for?
Yeah, of course.
Okay.
Okay, you need to know how is the inflow, so how large is the inflow, velocity or mass flow rate. Then you need the geometrical dimensions very exactly, that your model is exactly the same or at least as similar as it could be to the real world. And then you can simulate it, but then the simulation is also somehow, you have to model it correctly.
And then measure, so what's the correlation? How close you are able to guess with the model?
So for the wave, we did not do any measurements so far. So we just tried to include this baffle, and then we saw that actually the flow field behind the wave was much more stable, but just by looking at them, or you saw that blushing, and that was this was actually the flow which comes up, and this is typical.
Actually, the experience of the surfers.
Yeah.
I mean, this was like day and night difference. Actually,
yeah.
Like the feeling you had. This was very fantastic. How you could. Like seeing the picture beforehand, before we did the building or the adjustment of the construction, it really reflects what we felt in the water, and so the feeling afterwards, after installing this thing, chickenary you call it.
Yeah.
So it really reflected the pictures we got. This was a one-on-one correlation. This was really fantastic.
Yeah. Thank you.
But as I said, so measuring in that flow is quite difficult because placing sensors there is not that easy.
Here we can.
Yeah, hey, congratulations, that's great stuff. And kind of now you are using the CFD framework which is available in the university. So, and the relevant question, our approach was to use open source.
Open source.
Framework, so open phone, so that it's accessible for everyone.
Mm-hmm.
That is one idea. And the question here is about the organization of your project. That would be very valuable for this audience, that you do very high quality university academic research, and kind of the application for river waves would be so interesting universally. and how you have organized the situation that you have those students doing their master thesis and PhD studies around this.
You mean how we got these?
Where the resources come.
The resources come. So yeah, of course. This is not working, so I will talk loudly. So at the university, so we also using simulations in our normal respiratory flow analysis. So we purchased, or we got a quite good order, or we ordered the software from Siemens. It's Star CCM Plus from Siemens, which we are worked so far with. They have good conditions for universities because they want to have students educated with their code. So this is one thing. The other thing is that the high performance. So we have in Erlangen a high performance computing center where we have access for those educations, master thesis, and so on. And so this is in our university is quite the. So we need to have some all faculties, all institutes need to have some good topics, realistic topics to educate our engineering students for the work afterwards. So this is actually the organization. So we need to educate those students with tools that are available even after they graduated, and we got good conditions by the provider of this code, and we also have the scientific computing center where we have access to it and can also educate those students to work with that systems, because this is not just a computer, so you really have to handle those computers, or the composition of how many cores you need to calculate on, and how long it lasts to have a result and something like that.
Yeah,
so,
thank you.
Yeah.
Then I expect, or is it correct to assume that you will continue with this?
Yes.
Yeah.
Yes.
That's awesome. That's
for sure.
Really.
Yeah.
Great thing. And there, kind of my suggestion is that now you have the trimming piece, an additional trimming piece there. Mechanical engineering could kind of challenge could be to make that adjustable so that you don't need to dry up everything, so that you could adjust it on the fly.
Don't know whether I get the point.
So you have here the optimization algorithm.
Yeah.
And then the practical part of it is that now you adjust, kind of if you do the empirical side of the project and you put the additional part to the system, and then you verify empirically that it works, that kind of making the change in the wave is to make that adjustable.
So this wave in Nuremberg is somehow adjustable, also from the ramp and the kicker that is fully adjustable. Yeah. So everything behind is some. Yeah, of course. You can consider to implement some mechanical structure there, which you can manipulate somehow. Yes, of course, that is possible. But therefore, so actually at the moment we are at this point that we try to understand how to do it in a correct way, because also this solution what we have with this baffle is not the optimum actually. Of course, but this is so this is a process which we have to continue, and then
to answer that question, probably just to answer that question, we had another master student working on that, and we wanted to optimize the floor of the wave by optimization theory. Problem was that the costs of computation, because each step, each iteration, you have to recompute the entire flow field again. And when you think about that, we are around 100, 200 iterations times 12 hours.
Yeah.
Just slows, not possible. So we stuck.
I'm sorry, it's a very interesting topic apparently, but we are out of time. Thank you very much.
That was